All right. Now, this is the problem that has been given to us. There are three cubes given to us. And the first cube, the biggest, is side 3. So we have each side is given 3. The next cube is given side 2. And the last cube, the one on the top, the smallest, is side 1. And the problem is, if we can do this correctly, when I say if we can do this, I mean me, to go from that corner to this corner, if I can get there, I gotta rotate just a little bit more. This takes fine motor control that I don't have. And here we go. All right, that's the right angle. I just have to get the right position. There we go. That's good enough. So here we got a line that starts from this corner, and we go down. We drop down to the bottom corner. Okay, and lastly, we go this here. It's a matter of getting my line lined up properly. Okay, there we go. And what I'm going to do, I'm just going to draw a dotted line in this position to take it. Oops. Make sure we got our pen. There we go. So that gives you the idea. Now, what we're given is this triangle, and we are to find this segment. I probably should, I could, if I'm careful enough, I can go like this. Come on, I have to be careful about what I do. Okay, so we're going to drop a line over here. This is it right there. Got to get this angle right. And once we have, once we have that line up, I'm going to choose another color. Yeah, let's choose that. And that segment right there, we want to know what that segment is. Okay, I think that will pretty much give us what we want. I'm going to do a little cleanup. There. Okay, so the problem that we are given is find the length of the yellow section. I always, when I did this problem, I found that drawing the problem was more difficult than solving the problem. So, find the length of the yellow segment, and that's the problem. So, here, instead of trying to free draw, I want to note that we have a vertical there, and we're going to go down. We'll make it dotted. There we go. And then we've got the base here, which will be parallel. That should be parallel to that line there. And we'll go like this. Okay. All right, that's our triangle. And remember, this line, this dotted vertical line, is parallel to the corner of the cube. And this line penetrates the surface of the side 2 cube. And basically what we're doing here is we're using similar triangles to solve the problem. So we're going to have an angle here. We're going to call that angle theta. I'm not going to use similar. You see, now you'll find this online, and they don't specify how you can solve this. They solved it using similar triangles and reapplication of the Pythagorean theorem over and over again. I'm going to use a little trigonometry because that's the shortest way, and that is the most powerful method you've got. And it just makes this problem a whole lot more simple. But you're using the same basic principles, similar triangles. So you realize that this angle here, this angle here is also theta. That's what I mean by similar triangles. And so we have a right triangle that goes from the bottom cube, the base of the bottom cube, to the corner of the top cube, and the vertical on that, y, this blue line y, right there, and x is this, and we'll call this hypotenuse r, and that hypotenuse includes the yellow segment. So y is equal to 1 plus 2 plus 3, and that's 6. Now x, we've got 3 there and 3 there. And we use the Pythagorean theorem to find x. So x squared equals 3 squared plus 3 squared. And so x, well, we'll go x squared is 18. And x is the square root of 18. And 18 is 2 times 9, so we could say square root of 2 times 9. And, whoops, that wasn't so neat. Okay. Times 9. And that's equal to 3 square root of 2. Okay, so x is 3 square root of 2. We have the basic Pythagorean theorem, y squared plus x squared equals r squared. So we have 6 squared plus 3 square root of 2 squared equals r squared. So that's 36 plus 9 times 2 equals r squared. And of course that's 18, so 36 and 18, that's 14, 54. So r equals the square root of 54, which happens to be 9 times 6. So we got r equals the square root of 9 times 6, and that is 3 times the square root of 6. So that is our hypotenuse. Now we know that y over r is the sine of theta. So, oops, I've got a little bug walking on my screen. All right, so we're going to just use a little eraser here. Boom, get rid of that. Let's just put our summary up here. We just saw how we got it, so we got r equals 3 square root of 6, y equals 6, and x equals, what did we say x was? X was 3 square root of 2. And now we can erase this mess here because it takes up a lot of space. And I don't think I want to use 2 screens to solve this very simple problem. Okay, so now we've got the essentials. Now y over r equals sine theta. And so we have 6 over 3 times the square root of 6 equals sine theta. And that means we can simplify that a little bit more. We have 2 over the square root of 6 equals sine theta. And then theta is just the arc sine of 2 over the square root of 6. And theta is then, once we do the math, in just 1 second, I think it's 54.74 degrees. 54.74 degrees. I just want to confirm that. if my memory serves me well. Let's see, we've got 2 divided by 6 square root equals inverse sine 54.74. Okay, so my memory served me well. Now, that is theta, and we have similar triangles, so we have the same angle up here. So what we're looking for is y and y prime. Let's call it y prime and r, small r. Okay? And small r is the segment that we're looking for. So y prime over small r equals the sine of 54.74 degrees. Well, we know what y is, y prime. Y prime is 2. So we have r, just a little algebra, is equal to 2 divided by sine of 54.74 degrees, and that means that r is equal to, and we're going to take a look at this. We have 54.74 sine times 2. So we have 2.45. R equals 2.45. And we can say that this is x prime. So we can find x prime. And we've got y prime. Let's work over here where we have a little more room. Y prime squared plus x prime squared equals 2.45 squared. So x prime squared equals 2.45 squared minus 4, because 2 squared is 4. And so we square that. That's 6 minus 2 equals 4. So x squared equals 4. Or 2. I'm sorry. What am I doing? Let's go back here. All right. So we got 2.45 squared minus, squared minus 4 is 2. 2.45 squared minus 4 is 2. So we have 2, and x is square root of 2. So then we can say that y prime squared plus x prime squared equals r prime squared. And we have 4 plus 2 equals r prime squared. And so r is the square root of 6, which happens to be, when you take 6 and take the square root, is 2.45 when you round it up. So these are our answers, and you can see that they're correct by going to Presh Talwalkar and checking out his website. He gets the same answer. The only difference is that he just reapplies the Pythagorean theorem over and over and over again. He gets these long, very tedious means of coming to an answer, and using a little bit of trigonometry simplifies the problem a great deal, reduces the number of steps tremendously, and gives you the correct answer. Now, let's say if you were on an island and you were let's say a castaway on that island, and you needed to know what that segment was, you could reapply. You wouldn't have to know what the sine of 54 points. You wouldn't even need to know the angle. You just keep using similar triangles and the Pythagorean theorem, and you'll be able to find that segment. The only thing is that there is another way that you could approximate. Whoops, I don't know why I did that. You can approximate by actually doing something like this. You can create your own tabular. Whoops, we can. We'll just draw an XY coordinate system. Zip. We'll go zip, and we'll call this Y, X, Y, and we know that we've got when sine of pi on 2 is 1. So let's say that's 1. We can say that this is 1 on the x-axis, so we'll go 1 and 1. We know that sine of pi on 4 is square root of 2 on 2, and that just happens to be, if we go up like this and we go like that, that would give us 45 degrees. So we have something like that, and we can interpolate. We know that, for example, cosine of 60 degrees, and we could estimate, we know that this is 45 degrees. We know that 1/2 in the vertical is when you have 30 degrees, and so somewhere in this direction you got the sine of this is 30 degrees, 60 degrees. You could interpolate. It's 60 degrees. That will bring you to cosine of 60 degrees is 1/2. Sine of 30 degrees is 1/2, and you can go 60 degrees times pi on 180, so that's pi on 3. So we can start creating a table. Sine of pi on 2 is 1. Cosine of pi on 2 equals 0. sine of pi on 3 is equal, let's see, cosine of pi on 3 equals 1/2. And this is square root of 3 on 2, I think, something like that. We could find it later. And then we could say sine of pi on 4 equals the square root of 2 on 2. Cosine of pi on 4 is square root of 2 on 2. Then you got sine of 30, which is 30 is what? 30, 86 pi on 6. So pi on 6 equals square root of 3 on 2, cos of pi on... Wait a second, I made a mistake. All right, that's 1/2. And cosine of pi on 6 is square root of 3 on 2. And so on. Sine of 2 or 0 or 2 pi is 0. Cosine of 0 is 1. Same with 2 pi. And, you know, you can create yourself a little table and work these things out, and you could still use degrees. So, you know, you can, if you took the time, you could create yourself a little table of values for different angles, and you could work out the problem. So you don't always have to necessarily be powerless. With a little bit of knowledge, you can do some interpolating anyway. So 54, you could say, is somewhere 54.74 is less than 60, but it's greater than 45, and so you can come up with estimates like that, which will allow you to find out, you know, what the sine of 54.74 is. You would know that it's greater than square root of 2 on 2. It's in between square root of 2 on 2 and, well, let's say pi, if it's the sine of 54.74 and the sine of 60 is square root of 3 on 2. So you can estimate in between, you can interpolate this value. So you don't necessarily have to be stuck, nor do you necessarily have to have a calculator. You can use your head and a little linear interpolation to create a table and work it out. So there are various ways that you can approach this. Now, when I solved this problem, I did use what I felt was the most straightforward and simplest way of doing it. And, you know, you can use repeated applications of the Pythagorean theorem, but the more you square things, and again, with that, the problem with that is you have to estimate or interpolate square roots that are not necessarily. I mean, for example, using the Pythagorean theorem, I'm not going to necessarily know what the square root of 6 is. That the square root of 6 is 2.45. I'm going to have to go somewhere between the square root of 6 is somewhere between square root of 4 and the square root of 9, and so I would have to guesstimate anyway. So if I didn't have a calculator, it's a matter of interpolating anyway, and it may be less work interpolating angles, angular. For example, the sine of 54 degrees may be easier to interpolate than multiply trying to interpolate repeated square roots. And in fact, the more you interpolate, the more error you introduce into the solution. And so you are better off minimizing the amount of error that you're introducing into the problem. So I don't see the benefit of trying to solve something by using repeated applications of the Pythagorean theorem. I think the approach that we took here in this problem was superior, and it simplified the problem. In fact, the hardest part of this problem was actually drawing it. So anyway, if you have any questions on how to solve this problem, please leave your comments, and I'd be interested in knowing or seeing what you think when you compare my solution to how Presh-Talwalkar solved it. And by the way, Presh-Talwalkar uses, he doesn't call it the Pythagorean theorem, he calls it the Gauge rule. I've never heard of it before, but I mean, that would throw me way off, because I've never heard of this Gauge rule, and I looked it up, and it's the Chinese version of the Pythagorean theorem. It's the same thing mathematically. It's just that they don't use or attribute the name to Pythagoras. They use the Chinese name. But I've never heard it before, and no mathematician that I've ever listened to ever used that terminology. So that's something that is unique to that culture. And I am being swarmed by little fruit flies here. So anyway, this is Math Man wishing you the best.